All right, let's talk about temperature. We know things can get hot, right? I mean, really hot. The early universe was trillions of degrees. But what about the other way around? How cold can something possibly get? Is there a limit? Is there a bottom?
It sounds like a simple question, but the answer? Oh, the answer takes us right to the edge of what we know about physics, and it uncovers some of the weirdest stuff in the entire universe. But before we get to the weirdness, we've got to figure out what cold even is. Like, really, what is it? Okay, first things first, defining absolute zero. So, what is cold anyway? I mean, it feels like a real thing, right? Like, you can add cold to a room with an air conditioner, but in physics, it's actually the opposite. It's all about what's not there. And that right there is the absolute key. See, heat is a form of energy. You can add more of it, you can keep piling it on, but cold, it's not a thing. It's not a substance. Cold is just what's left over when you take the heat away. You can't add cold to something, you can only remove the heat. This brings up a really important point that trips people up all the time. The difference between temperature and heat. They're not the same thing. Temperature, that's the average energy of all the little vibrating particles. Heat is the total energy. So think about it like this. That cup of coffee you had this morning has a really high temperature. But the entire Atlantic Ocean, it has way, way more total heat energy, even though it's much colder. So if you can keep taking heat away and away and away, a physicist named Lord Kelvin had this brilliant realization. There has to be a bottom, a point where you've taken all the heat out and there's just nothing left to remove, an absolute floor for temperature. And he called it, you guessed it, absolute zero. He even created a whole new temperature scale, the Kelvin scale, that starts right there. And just to put that in perspective for us, on the Celsius scale we're used to, that rock bottom temperature is minus 273 degrees. That's 0 Kelvin. I mean, that is colder than the emptiest, darkest parts of deep space. It's the ultimate cold. All right, so now we're talking about the unreachable temperature. We have our target, right? 0 Kelvin. We have this theoretical limit, but how do you actually do that? How do you suck every last drop of heat out of an object? Well, the basic idea is pretty simple. It's actually how your fridge works. Heat always wants to flow from something hot to something cold. So if you want to make an object colder, you just put it next to something that's even colder than it is. The heat gets pulled away. And then you just repeat that. You find something even colder and do it again and again. And you probably see the problem here, right? It's a bit of a catch-22. To pull that very last bit of heat out of your object to get it to absolute zero, you'd need something that's already at absolute zero to do the pulling. It's a classic paradox. You can get ridiculously mind-bogglingly close, but you can never, ever actually touch that finish line. But here's the thing. That little logic puzzle, that's not even the main reason we can't get there. It's almost like a friendly warning from the universe, because the real problem, the real roadblock, is something much, much weirder. Yep, this is where quantum physics takes over. We have to throw out all our normal, everyday ideas about how the world works. Because when you get down to the level of single atoms and particles, the rules completely change. And here's the absolute kicker. In quantum physics, nothing is ever truly stationary, ever. Particles always have a tiny bit of energy, a fundamental jiggle that you can never, ever get rid of. It's like a constant quantum hum throughout the universe. To get a particle to be perfectly still, you'd have to know its exact position and its exact motion at the same time. And the universe simply has a fundamental rule against that. It's an unbreakable law of reality. So let's move on to this world of weirdness. We've established that we can't actually reach absolute zero. It's impossible. But what's so cool, what's so fascinating, is what happens when we try. The journey towards zero has revealed that the colder things get, the weirder they get. Okay, get ready for your mind to bend a little. Every single particle also acts like a wave. It's just a quantum thing. Now, when a particle's hot and has a lot of energy, it's vibrating like crazy, and its little quantum wave is short and tight. But as you pull that energy out, as you cool it down, that wave starts to stretch. It gets longer and longer and longer. So what happens if you take a whole bunch of particles and cool them all down at the same time? Well, all of their individual waves start stretching out, so much that they actually start to overlap with each other. And when they overlap, something amazing happens. They stop being individual particles and start acting like one single giant quantum object. It's like a huge flock of birds turning and moving in perfect unison. And this bizarre, synchronized behavior creates entirely new states of matter. I'm not talking about solid, liquid, or gas. This is something else entirely. We've discovered things like Bose-Einstein condensates, superfluidity, superconductivity, things where the laws of physics as we know them just seem to break. Just take superfluidity, for example. It's a liquid with literally zero friction, zero. You could stir it, and it would just keep swirling forever. It can climb up the walls of its container and escape. It's like something out of a sci-fi movie, but it's real, and it's all thanks to the weird quantum rules that take over in the extreme cold. Okay, this brings us to the big question, right? Why does chasing zero even matter? If we already know it's impossible to get there, why are we pouring all this time and money and brain power into trying?
I mean, you can just imagine some physicists asking for funding, saying, "Hey, I just want to play with cool temperatures and see what happens." You'd probably think, what's the point of that? It can seem like just a game, right? But that totally misses the whole point of science.
See, the real point of all this is that when you push the absolute boundaries of what's possible, when you chase these fundamental limits of the universe, you find things. You stumble upon truths you never, ever would have thought to even look for. I mean, who would have ever thought that these incredible, extraordinary new states of matter were just sitting there, hiding out at the coldest temperatures, just waiting for us to find them? Nobody set out to invent a superfluid. It was discovered by pure, relentless curiosity. And really, that's the beautiful takeaway here. The goal isn't actually to reach absolute zero. We know we can't. The real prize is all the mind-blowing stuff we discover on the journey there. It just makes you wonder, doesn't it? What other incredible realities are out there waiting for us at the next frontier of science?